Hello, everyone. Welcome back. We are continuing our journey in glass technology as part of Chapter 2 of Fundamentals of Inorganic Glasses. Last time we covered glass melting, and today we are going to get into glass forming, specifically some of the common techniques for forming sheet glass, tubing, and glass hollowware. So let's dive in. As just a reminder, the various stages of industrial glass manufacturing start off with batching. This is selecting the appropriate batch materials, mixing them together. Then they go into the melter, and we need to make sure that we can melt everything completely and homogeneously while minimizing any solid gaseous defects and also minimizing any inhomogeneities. The gaseous defects are taken care of in the finer, where we've got both physical fining and chemical fining. Physical fining enlarges the size of the blisters so they rise up faster, and then chemical fining reabsorbs remaining oxygen as the glass cools down. Next up is the forming operations. This is where we take our nice, homogeneous, fully melted glass and then form it in the shapes that we want to obtain. So we'll be covering that today. And then after forming, there may or may not be finishing operations, annealing, other post-treatment that is done on the as-formed glass. So if we go back to the old days, one of the old methods of forming glass was called the crown process. And with the crown process, a gob of glass would be put at the end of this rod, and then it would spin around. And the centrifugal force would cause the gob to spread out as kind of a disc shape. And then what the glassmaker would do would be to take that disc and then divide it up into certain regions here where they could make glass that isn't really flat, but it kind of approximates flat glass in different regions. But of course, we know that the glass would be thicker in the middle part compared to the outer part, and therefore you could never really get very good thickness control with an operation like this. And this is why if you look at glass windows from hundreds of years ago, for example, you will see thickness variations there because of the means by which that glass was made, that some parts would be thicker compared to others. Some people have purported that the glass might be flowing over time, but the more likely scenario is that it was thicker in one part to begin with. So one of the more modern processes for making flat glass is the Boudin continuous double roll process. With this process, the molten glass comes out horizontally from the forehearth. This is the tank glass level here. And then the molten glass flows through these two rollers. So you've got one roller that is going this way, the other roller that is spinning the other way. And the molten glass passes through the rollers, and this gives you pretty good thickness control where you can adjust the spacing between the rollers to adjust the desired thickness of the glass. And then you've got a fairly uniform thickness sheet of glass that comes out the other side. The glass comes onto rollers and then gets pulled into latter parts of the process. Um, Now, the problem with this process is that the molten glass is touching a solid material on both sides because the rollers are solid materials. The rollers are going to have imperfections, surface texturing, and all of those imperfections and texturing get impressed into the surface of the glass. So even though you get good thickness control with this process, the surface quality is actually not that great because all of the glass is being pressed through these solid rollers. So any surface imperfections get imprinted into the glass, and then you don't have a nice, perfectly smooth glass surface as you would want to have. Another process that has been used in the past is the Fourcoult updraw process. Instead of rolling out the glass horizontally, what the updraw process does is that you've got a glass melter here at the bottom, and then there is kind of a mold here called a debuteuse, and the molten glass is pulled upward out of the debuteuse into a sheet. And then there are rollers on either side of the sheet that help to pull it up such that the interior part of the glass doesn't touch the rollers, but it is still touched by a solid material because the debutus here is what is forming the glass in its particular sheet geometry. And so the glass is passing through this debutus, and any imperfections from that get imprinted onto the sheet. The other problem with the Fourcoult updraw process is, what if the glass breaks? It's being pulled upward, it's cooling as it goes upward and going through the glass transition and becoming solid over time. If the glass breaks, it all comes crashing downward onto the process, and it creates a mess, and it's actually very difficult to restart this process up again. So this isn't used very often anymore. You can see here is a cross section here of the slot form that is at the top here of the W2, so you can see how the sheet geometry comes out by pulling upwards. A more modern process that is still very much used today is the Corning fusion draw process. The Corning fusion draw process was developed starting in the 1950s at Corning Glass Works. And with this process, there is molten glass that is delivered onto the top of this ceramic material, which is called an isopipe. This isopipe is, can be made out of different types of ceramics, such as zircon is the most popular choice. Alumina can also be used. And then the molten glass is delivered at the top through this trough, and then it overflows either side of the isopipe. It flows downward on the right side of the isopipe, and it flows downward on the left side of the isopipe. And then the two sides fuse at the bottom of the isopipe into a sheet. That happens at the root of the isopipe at the bottom, and then the sheet is drawn downward with using under the force of gravity, as well as rollers that are on either side. And the nice thing about the Corning fusion draw process is that neither of the final surfaces has touched anything other than air. So the only part that touches the solid is actually at the interior, at the so-called fusion line of the sheet glass. So if you've got half of it going out to the right, half of it going out to the left, the part here on the right that has touched the isopipe ends up in the interior. Likewise, the part on the left that has touched the isopipe ends up at the interior as it overflows both sides, comes down, and then fuses at the bottom. The outside surfaces of the sheet have touched nothing other than air. And so with this Corning fusion draw process, you have perfectly pristine surface quality on both sides. The fusion draw process also gives excellent thickness control. It's also very adept at making really thin sheets of glass. And basically, the faster that you pull it down, the thinner the sheets can get. Um, and so it's a really efficient process with great control and great surface quality. It is a vertical process, which means that you need to have enough vertical room in your factories to support this process. Normally, the glass melting, the batching and the melting is done at the top floor, then it's delivered onto the next floor down for the fusion draw machine here, and then the sheet is pulled down to the bottom of the draw, where the sheet gets scribed and cut, then sent on for quality control. I can show you a video here. Let me switch over to my web browser, and I can show you the Corning fusion draw process here. This is a video that captures some of it. This is Corning's proprietary fusion draw process, which is how all of their Gorilla Glass is made and display glasses. This is not a very good representation of the melter because obviously it's not open and you don't have the batch materials flying into it. But the glass melting takes place at temperatures of around 1600 or 1650 degrees C. The melt actually kind of feeds in from the side into the isopipe, not on top, and then it overflows either side and then fuses down at the root of the isopipe into a sheet. Then this sheet is being brought down. At the bottom of the draw, there's this machine here called a traveling anvil machine that grabs it with suction and then has a scribe that goes across. And the scribe runs across, the traveling anvil machine puts that scribe mark into tension so the sheet can be broken off. And then the sheet goes onto a conveyor belt where it goes through quality control. If it passes quality control, everything is good. If it doesn't pass quality control, then the sheet gets dropped into the next floor below where it becomes colored. So this is one of the two main processes by which sheet glass is made today. The other process is the Pilkington float process, which was developed around the same time by Alistair Pilkington at Pilkington Brothers in the UK. Whereas the fusion draw process is a vertical process, the Pilkington float process is a horizontal process. And the idea with the float process is that the molten glass is floated on top of a bath of molten tin. Because of the lower density of the molten glass compared to the molten tin, the molten glass floats on top of the bath of molten tin. The glass spreads out across this molten tin bath, and you get good thickness control based on how fast you pull the molten glass across that bath. So the molten glass is delivered, it floats on top of the tin, and then it gradually cools as the glass progresses horizontally across the molten tin bath. All of this needs to be done with a controlled atmosphere because the tin is a metal, and so we cannot expose that to an oxidizing environment. Otherwise, it would react and form tin oxide. And so even though the fusion draw process is done in air, the flow process needs to be done in a reducing atmosphere. So it is an N2 plus H2 atmosphere to make sure that the tin stays in its reduced metallic state. And then the glass slowly cools. As it cools, the viscosity goes up, and eventually the viscosity is high enough that it can be pulled off of the molten tin and onto rollers. This process also gives you really good surface quality because the upper surface of the glass doesn't touch anything but air, and the lower surface is touching a liquid rather than a solid, so it's touching molten tin. There is kind of a non-uniformity between the two sides of the glass, though. There is an air side of the glass that touches the air, and then there's a tin side of the glass where a small amount of diffusion of tin from the tin bath can go into the float glass. And you can see this because tin actually fluoresces a little bit under UV. And this is the process by which all architectural glass is made now too. So if you look at architectural glass under UV, you can see that one side is going to glow a little bit, fluoresce a little bit due to the presence of tin on one side. This process is a very economical way to make very large sheets of glass. This is adopted now for essentially all architectural glass worldwide, and almost all automotive glass is also made via the float process, where it starts off as flat glass, but then the flat glass is slumped either into a mold or under gravity in order to form the shape that's needed for automotive windshields. So the float process, again, let me switch back to YouTube here. The float process, here's a video here from Pilkington um, that shows the main steps of the float process here. This shows the glass going over the rollers. Let me jump ahead a little bit. You can see the sheets of glass going across the rollers. And if we start off, here is the batching of the batch materials. So here's some of the cullet that is incorporated into the batch. So that's the crushed up pieces of recycled glass. They get put together with the crystalline batch materials that are crushed together and then fed into the batch. The melting process, you can see here's the batch that is going into the melter. The batch is being pushed into the melter at a specific rate. And there's a little window here to see how hot it is there in the melter. You can see the environment here is just very extreme because of the high temperatures. This shows kind of the roofs of the melters. This is the furnace control room that controls all of the temperatures of the furnaces and the forming process as well. Here, these are gas burners that are used for most flow processes. Here you can see the gas burners above the melt line of the glass. And then, so this is a hot crown configuration because of the gas melters. So it's hotter on top, colder on the bottom. There's convection um, that leads to homogenization. And then after melting, it's delivered to the tin bath. So here's the melter, and this is being delivered. There's actually a two-stage melter here, and this is being delivered to the tin bath. So the molten glass is spread out on top of the tin bath. And here you can see the sheet of glass that is floating on top of the tin. And when it comes off, you can see the sheet of glass that comes off of the conveyor rolls. So that's kind of an overview of the Pilkington float process. Pilkington took the opposite approach compared to Corning with their design. So even though Corning kept theirs internal, Pilkington licensed their float glass technology to a lot of other glass manufacturers. So that is why it has become so ubiquitous. And there are a lot of companies now that manufacture glass via the float process. Next, the next machine I want to review is the ribbon machine, which is used for making incandescent um, light bulb envelopes. So when Thomas Edison invented the light bulb, he didn't have a process for making the glass envelope that could keep the light bulb sealed. And so he actually went to Corning Glassworks to figure out a process for making this. And Corning invented this ribbon machine, which is a process for making these output. This is more than 1 million bulbs per day using this ribbon machine. So it's a very inexpensive way to make a large number of light bulb envelopes. And this is why electricity and artificial lighting could be used not just by the very rich people, but by common everyday citizens. And this is why we have artificial lighting everywhere today. And all of that is due to this glass process innovation for the ribbon machine. With the ribbon machine, there is a thin ribbon of molten glass that is spread out over this conveyor belt that has little holes in it as well. And then there are blowers here that blow into this in order to blow out the envelope of the light bulb. That is caught on this other conveyor belt here to make sure that we get the right shape. And then these bulbs are delivered here. Once they're cooled enough, they're delivered onto a conveyor. I'm going to show you a video because that will show it better than this drawing. So this is a video made by Corning Museum of Glass that shows the ribbon machine in action. Here you can see the envelopes here, the glass light bulb envelopes going across. It's going so fast you can hardly see it, so the video slows down a bit to show this a bit better. But here you can see the blowing process of the glass ribbon starting to be blown out and forming the shape of the light bulbs. And then this other conveyor comes in and is going to provide basically catch it on the other side and make sure that we get the right shape. This whole process is kind of insanely fast. Here you can see the light bulbs after they've been formed into the right shape. Then as we continue on, let's see. Here you can see the light bulbs coming out at the end of the process. So it is a very impressive process for making a huge number of light bulbs very quickly. So that is the ribbon machine. Now, for making glass bottles are made using either the blow and blow process or the press and blow process with this individual section machine. And basically, it's a two-stage process where there's either a blowing process or a pressing process followed by a blowing process. So there is a gob of glass that is delivered into an initial mold. In that initial mold, it's either blown or pressed into that initial mold. That forms what's called a parison, which is kind of a partially formed glass bottle. That parison gets transferred into a finishing mold, and then there's a blowing process in the finishing mold that blows out the parison into the final bottle form. So this is the most popular one is the blow and blow technique called the Hartford individual section or IS machine, and that is the process that is shown here on the right. In these press and blow method, a plunger is used for the initial step instead of blowing. So basically, there are two molds. There's the initial mold and then the finishing mold, either pressing or blowing into the first mold, and then transfer into the finishing mold where it is finalized. Here's a video that shows the glass bottle video. This, I believe, is coming from uh, Owens, Illinois, and this will show you the glass bottle machine in action. Okay, here we go. Sorry for that ad. Now you can see the batch materials being pushed into the melter here. So this is our mixed batch material that's being pushed into the melter. And now the glass gobs. So the glass is being delivered and it's being cut into gobs of appropriate sizes. Those gobs are being delivered into, see, they're going to be dropped. Isn't that cool? It directs it into different molds here. Um, Then there is a blowing operation that occurs in the initial mold, and then that parison that's formed is being transferred into the final mold. You can see the parison being transformed into the final mold, and then the blowing. See, the blowing operation is taking place right here, and that is getting the final shape of the bottle. And then those bottles are being transferred. There we go. The initial parison being transferred. There we get the bottle. Here's the finishing mold. It's blown out into the bottle shape, and then they are continued to cool. As these bottles continue to work their way through the process, they're going to cool. They're going to go through a quality control step. If they pass quality control, they continue on. If they fail quality control, then they'll be dropped and then crushed up into cullet again. When it comes to glass bottles, another important part of this is to make sure that there's nothing sharp or rough on the lip of the bottle itself, because you don't want to cut yourself when you're drinking from a bottle. And so one of the finishing steps for glass bottles is some fire polishing that gets done on the lip of the bottle itself. And I think they're going to show that up ahead in a little bit. So all these bottles, there's some quality control here, looking at these bottles optically. All in a line along their conveyor belt. Oh, here the looks like the caps. Oh, here we go. This is the finishing part. Oh, the quality control part. They're optically scanning these to see if there are any defects there. And if they pass quality control, they will continue on. And all the bottles together here. So yeah, that's a really remarkable process for making these. Continuing on, let's move on now to glass tubing and glass rods. There are two kind of related processes for making glass tubing and glass rods called the Danner process and the Vello process. With the Danner process here, the molten glass is delivered from the forehearth and it is poured onto this sleeve. The sleeve is rotating such that the molten glass completely covers the sleeve. And then there is air that gets blown into this, and then the glass gets pulled down across the sleeve with air blowing through it. And the more air that blows through it, the more that the tubing opens up to get a greater inner diameter to the glass tubing. As this tubing is pulled down, it's cooling down and the viscosity is increasing. Eventually, it becomes rigid enough that it can be supported onto these line supports here and go across this conveyor. There's usually something here that would cut this off to get particular sizes of the tubing. And you can control the pull rate here and control the air pressure that goes in to control the geometry of the tube. The other thing you can do is instead of making hollow tubing, if you want to make a solid rod, you use the same process here, but instead of blowing air, you just pull a slight vacuum here. And if you pull a slight vacuum, then that will pull this glass tubing closed. And when you pull it closed, it becomes a solid rod instead of a tube. And then the rod continues down and goes across the conveyor here. The Vello process is kind of a variation on this theme. Again, there's blowing air that goes in to make tubing, or you can pull a slight vacuum here to make a rod. Either way, the difference is that now the glass is coming down vertically. Instead of onto a sleeve, it passes um, around this bell-shaped thing here, and the glass comes around this bell, and either air is blown into it to open it up as a tube, or there's a slight vacuum to close it up as a rod. And then the tubing or the rod comes down. It's bent around horizontally here, cooling as it comes down, and then gets cut off at the bottom. So these are just two variations on kind of a common theme for making glass tubing or glass rods. So that does it for this particular lecture. We will continue next time and look at the process for making fibers. All right, thank you everyone. See you next time.